This video will provide an overview of our new battery setup tool in Oasys Primer 21. The LS-DYNA EM solver offers the option to simulate the internal electrochemical reactions of a battery cell through the random circuit capabilities, which could be used to analyze its thermal response during the charge or discharge cycles, as well as predict internal short circuits during abusive scenarios. However, setting up a battery cell model manually can be tricky and time-consuming and requires a comprehensive understanding of the different LS-DYNA random circuit modeling options and requirements. The process involves meshing the layer cell structure and the tab structure, connecting the tabs to the layer cell structurally and electrically, defining the electromagnetic properties of the different components, as well as defining the random parameters and relevant analysis keywords. The battery setup tool was introduced in Primer to expedite the creation of random circuit-based cell models and guide you through the different stages of model creation. The first step is to select the random circuit modeling scale, which determines the level of modeling detail of the cell components, as well as the EM randos keyword used. The micro, meso, and macro scales require physical modeling of the battery cell, while the meshless scale models floating random circuits and can either be used in solitary state or connected to a macro structure. Once the modeling scale is selected, the structure of the layer cell can then be created by defining its properties. For the microscale, 5 solid parts will be meshed per unit cell, representing the 5 cell layers: a positive current collector, a cathode, a separator, a nanode, and a negative current collector. For the mesoscale, a composite T-shell part will be meshed per unit cell with customizable number of layers. For the macroscale, a single solid part will be meshed per unit cell. For all modeling scales, multiple repetitions of the unit cell can be created. The structural material ID and thermal material ID of the cell components must be defined, and an EM math card will automatically be generated by Primer with its type depending on the selected scale, in order to define the electromagnetic type and properties of each component material. The third step involves creating the tab structure. For the microscale, the positive tab will span the positive current collector, while the negative tab will span the negative current collector. For the macro and mesoscales, both tabs will span the whole unit cell. 4 different configurations of tab positioning relative to the layer's unit cell are available to select from. The tool offers the option to structurally connect tabs to the layer cell by automatically creating a nodal rigid body for each tab to cell connection that includes overlapping nodes. The tool can also electrically connect the tabs to the layer cell by automatically generating EM isopotential instances to constrain the overlapping nodes to have the same scalar potential value. Isopotentials can also be generated at the free surfaces of the tabs, which could then be easily used to interconnect the different tabs or to connect the tabs to external circuits using EM isopotential connect cards. The next step involves generating the relevant EM randos keyword to model the battery internal random circuits. Primer will automatically set the fields defining the cell structure parts or part sets created during previous stages, but all other fields will need to be provided in this panel. If in meshes connected to macrostructure mode, for each unit cell, 2 EM isopotential instances will be generated containing the tab nodes overlapping with the cell, and the 2 EM isopotentials will be connected through an EM isopotential connect, referencing the associated EM randos meshless entry. In the fifth and final step, the tool offers the option to select from a list of relevant analysis keywords. The main fields can be set in this panel before generating the keywords. All other parameters can then be edited through the Keyword Modify panel using the Edit buttons. The data from all 5 steps can be exported to a CSV file in the Analysis panel and imported back into future sessions in the Geometry and Scale panel. As an example, the shown D3 plot results were produced for a simple macro battery model generated by the tool to analyze the discharge thermal response due to internal resistance. Thank you.